I will not talk about those rules. It's your responsibility to know the rules of the course, which is available at the module page. Okay, let's go back to the course topics again. We said that there are two reasons why we need operating system. The first one is abstracting the hardware. Okay, this is very important. This is very important because this is the whole reason why we are studying this course. Okay, we are taking this course. The first one is this one, abstracting the hardware, because we say that hardware is very difficult to understand by a single person. Okay, there are very different types of hardware, like the printers or the screens or the network devices or the sound devices or the video devices, etc. As you know, there are very large number of output or input devices available for a computer, and each one has a very difficult to understand interface. So if I don't abstract those interfaces, if I wanted to use all of those hardware elements directly, then that would be a problem. Remember the last time we talked about even a single line of printf hello world takes 1 million lines of code if you wanted to do it all by yourself. So we should abstract the hardware so that programming a computer is easier, so that a 10-year-old person can program the computer by writing printf hello world. Okay? So that's one of the reasons why we have operating system. The second one is the managing the resources. Okay, the computer has many resources, like the processors. You may have more than one processor, or a single processor. You can time share it. We have lots of memory, but it has to be managed. We have timers, we have disks and mice and etc. They have all those resources and input-output devices, and they have to be managed. What do I mean by managed? We have many programs running on the computer at the same time. So when they are running, they should not use each other's space, memory space or the disk space, or they should not use each other's CPU slice, time slice, and these should be enforced by the operating system. Otherwise, if there is how many processes are running on this computer right now? Last time we checked it. How many processes are running? There are 60 or something, right? And I am not running anything. I am just running this PDF viewer, okay? Other than this PDF viewer, there are more than 60 programs running, doing some kind of work. I don't know what they are doing. If I wanted to do many things, if I wanted to do more things on this computer, then that means that there will be more than 100 processes on this single personal computer. If you think about the servers and the mainframes, there might be thousands of processes or programs running. And if one of them is behaving badly, that means it is trying to use somebody else's resources, then operating system should interfere and say that, okay, you cannot do that. So it has to be done. Somebody has to do it. Operating systems are doing this. They are managing the programs so that they can work in synchronization without any problems, like the protection errors and that kind of stuff. So, two things. As I said last time, if you don't remember anything from this course after you take it, then you take a passing grade. If you don't remember anything, just remember these two. Operating systems, what's an operating system? It's a slice of software between the hardware and the application programs. Okay, between the hardware and the application programs, it's a piece of software. It's a large piece of software, but still, it's a piece of software, and its job is to abstract the hardware for the application programs and manage the resources that the computer has. Okay, just these 2-3 sentences. Just remember these. Okay. Of course, if you write these down in the final exam, what you're going to get is 5 out of 100, because I will be asking lots of more detailed questions. But at the end of the courses, in 2 or 3 years, I expect at least to remember these 3 simple things. Okay, I forgot to bring the attendance sheet, So remind me next class, the next hour to bring it again. So it's kind of a review, so I will skip the rest of it. And we talk about this. Remember, we said that there is a for a software, for a computer, there are two modes. One is the kernel mode, the other one is the user mode. Okay. What is the difference? In the kernel mode, a program can do anything it wants. Okay, a program can do anything it wants, writing anywhere, reading from anywhere, and accessing any I/O device in the kernel mode. In the user mode, those kind of stuff are forbidden. The user mode programs, if a program is running in the user mode, then user mode programs are limited in that you cannot directly access the hardware. Okay, you cannot write anywhere you like. You cannot read from any device you like, so it is restricted. Operating systems run in kernel mode, okay? Unless your computer is very, very primitive computer, like a real-time computer, embedded computer. In the user mode, all the application programs and some part of the operating system actually, some part of the operating system runs in the user mode. So the computer has two modes. Remember this, and most of the time when we talk about an operating system, we will mean this part. We will mean the part of the operating system that runs in the kernel mode. Okay, we talked about this, that nice picture, and you read your from your book. And we were talking about this history of the operating systems. And I said that history is a very big part of the operating system, okay? Because whatever we do, whatever technique I am going to talk about, it was a solution to some problem, okay? And those problems are defined by the history. By history, I don't mean 15th century history. I mean our history starts in the operating systems in 1945 in the World War II area, okay? And in the first 10 years, we didn't have a much operating system actually. You have very large computers, and they were running with the vacuum tubes, very, very large transistors, if you like. We can define it like that way. And the operating systems, there were no operating system. The programmer takes the whole computer, which is very, very, very large, as large as 2-3 rooms and hundreds of tons actually. And it takes lots of power to run those computers. And the programmer programs the computer by either pushing the switches or connecting some cables. Then it runs it, his program. If the results are okay, then he's okay. Otherwise, he has to change those switches or the cables. So he has the whole computer to himself. By the way, those computers are like tens of millions of dollars computers. And while the person is working on the computer, nobody else can use it. So it is very expensive to use that computer even for an hour. So that was the case in 1945 to 55. So in the first 10 years, we didn't have much operating system software. Then in 1955, we started using them, and the real story started in this date, 1965. So the third generation computers or the operating systems are the real operating systems. And in fact, whatever we are using today as an operating system concept, it was invented in this area, okay, from 1965 to 1975. All the things were invented in those days. Some of them are primitive, some of them are very, very advanced, but we didn't invent much after those days. Even cloud computing, okay? I mean, we think that cloud computing is something new. No, in 1960s, this operating system, the whole purpose of this operating system, Maltex, is to do cloud computing. He says that General Electric, and AT&T and MIT, these three institutions, they said that we can provide computing power to homes like we are providing electricity to homes or the water to homes. I mean, I buy water from the utility companies or electricity. I can buy computing too. So they were trying to achieve that one, and they actually achieved it. So there were some marketing problems and everything. So most of the cloud computing ideas and the techniques and the problems, it was all invented during those days. This wasn't This was used by many companies, but it wasn't a very successful operating system. But later, they modified this operating system. They modified this operating system. They made it simpler, and they call it Unix. Okay, so Unix is a descendant of this operating system. Then later, from the Unix, we have Linux, and from the Linux, we have Android. Okay, so the Android roots are from these days. See, whatever I talk about modern operating systems, the Windows or the Mac OS or the Android or the iOS, whatever, their ideas are not new. Their ideas are all invented during these days and these days. Okay, so we will be talking more. We will be spending many minutes talking about the history. So you should do the same thing. Read the history about the operating systems. And 1980s to present and 1990s to present. 1980s it was the time for the large-scale integration. Okay, large-scale integration. We have chips. You can put many transistors in the same chip. It is much cheaper. It runs much cooler, less power, and it is much smaller. You can fit it on a small motherboard. And these operating systems. Disk operating systems and the Windows and the Macintosh operating system and the variants of the Unix operating system. And from 1990s we had the mobile computers. Mobile computer is a computer, a small computer, but they are not. They are more powerful than the computers of these two areas. Okay, so they are computers. They are the less powerful computers. They are still more powerful than these two types of computers, which cost like tens of millions of dollars. Okay, so the new problem for these kind of computers is the power management. Up to this time, we didn't have any power management issue because we just plug our computer to the wall and it just worked. We didn't care about how much power it takes. With the mobile computers and some of the server farms, you know this term server farm, right? Server farm. What's a server farm? What's that for server farm? It's a farm with servers. Okay, even you laughed at it, but I get these kind of answers all the time from the exams. So I laugh at them. So what is the answer? What's a server farm? Google has lots of them. Facebook has lots of them. Söyleyemeyiniz, neye bakıyorsunuz ya öyle? Önüne bakan diyor, okutan diyor.
Hocam bir sürü bilgisayar bir yerde duruyor.
Aynı işi yapan bir sürü bilgisayar bir yerde duruyor. Evet. Yani aynen şey gibi, tavuk çiftliği gibi. Hiçbirinin birbirinden farkı yok. Hepsi kaderi aynı, kesilecekler, şunu yapacaklar. Server farm böyle. Birbirine hiçbir farkı olmayan yüzlerce, binlerce, on binlerce bilgisayar aynı yerdeler. Bu server farmların önemli problemlerinden bir tanesi, what are the problems with the server farms? Different from the other computers.
Soğutma ve enerji.
Yes, energy, power. They take lots of power, and since they are taking power, they produce lots of heat. So you need to cool them down. That's why they try to build their server farms near the power generators, near the dams or the gas generators, so that they can buy the electricity for cheap. Okay, and they sometimes what they do is they try to build their server farms underwater, so that they can easily cool them down. Okay, there was one solution. One guy said that, okay, don't cool the servers down. Okay, let them run hot. If they run hot, they will die maybe 1 or 2 years early. That's okay. In 1 or 2 years, we are going to change them anyway. So some of them are not cooling them down. That's the solution. So these kind of problems did not exist in these three areas. Okay, we have these problems after 2000, since it is invention of the internet of the cloud computing and the mobile computer. Mobile computers, power is everything. I mean, if you have a computer which can do anything you like, but the battery life is like 15 minutes, nobody is going to use it. We didn't have such a problem previous. Other than that, multi-programming, multitasking, protection, abstraction, user interfaces, graphical user interfaces, they were all invented in 1960s. Okay, in 1960s. Okay, so 1945 to 55, vacuum tubes. Okay, I took this from last night from Wikipedia. Vacuum tubes are like this. Each one is kind of a transistor. Okay, what's a transistor? It's transistor like a valve. It controls the current flow. So these are centimeters. It's like so. This part is like maybe 2-3 centimeters wide, maybe 6 centimeters tall. But each one is just a single transistor. Nowadays, each transistor is like 10 microns, right? It's smaller than 10 microns. These are large transistors. We have many much smaller transistors than those micron level transistors. In 1940s and 50s, we have transistors like this, and they use lots of power. They use lots of power. In fact, this computer ENIAC, you know, this is computer ENIAC. Each of these are vacuum tubes. Okay, they were installed like that, and it had near almost 18,000 vacuum tubes. That means that you have a computer with 18,000 transistors, which is not a very big number. Okay, we don't have such computers anymore. So our number of transistors is much higher than that. But it used to consume this kind of power, 150 kilowatts of power, which is you can have all this kind of power only with the industrial energy lines, okay, power lines. So it produces lots of heat, and every 10 or 15 minutes or 20 minutes, one of these vacuum tubes stopped working, so it had to be replaced. So your programs can run at most half an hour. After half an hour, you have to change one of those vacuum tubes. So they didn't have an operating system because the computers were very primitive. Okay, so they are very weak. They didn't have enough power, and since they didn't have enough power, you cannot run extra programs on them. And as you know, operating system is a slice of software, or a piece of software. You cannot have two programs running on the same computer. So you cannot have complicated operating systems, at least. Okay. So when you are running your programs, it's a dedicated time only, and it is manually managed. You go to the computer room, you push switches, and you change your switch. That means it is like that. Okay. Memory is something like this, right? I always draw memory like that in my programming courses or whatever. Memory is like that. The memory for these kind of computers like that too. So they divided the memory like this, and for each bit, these are the bits. There is a switch. Okay. If the switch is like that, it is 1. If the switch is like that, it is 0. Okay. You can think it like that. So it means that 1 0 1 0 1. If you want to put this information into memory, you need to manually switch those switches to proper positions. Okay. This is how you program your computer. Okay. And once you program your computer with those ones and zeros, or sometimes they use the decimal system. Instead of 1 0, they have decimal system from 0 to 10, 0 to 9. ENIAC use a decimal system. You let your program run, and after a while you get your results in the memory, and you print it out, and that was your solution. And this was very painful. So second generation, instead of using those switches, they started using punch cards, which is like that. Okay. So you punch your program in a card like that. Okay, this is a card. This is a card paper, a thick paper. So you put holes in the paper like that. Okay, there's a 1 and 2. In the third column, I think there is nothing. And in the seventh column, this one, is this same? Okay, so I don't see anything in the fourth, fifth, and sixth column. Seventh column I have 7, then 9. So you program your computer using this punch card. Instead of switching those things, okay, you put holes into the card, okay. So this is how many? This is like 80 words, okay, 80 bytes if you like. 80 bytes of code, not 80 lines of code. It's because we don't have compilers anymore yet, okay. So 80 bytes of code, and if you have many cards, you punch them out, and you feed them into the computer. There is a punch card reader. It reads your punch cards and it puts all that information into the memory or in some tape, magnetic tape. It's stored there, and then this is what you do. You get your punch cards. Let me show you some deck of punch cards. These are deck of punch cards, okay? There are how many punch cards here? Maybe 200 punch cards, okay? So in the first punch card, you have this information. It's my job number, and there are some numbers and the name of the person writing it. And this one says that this program will run with the Fortran compiler, which is the first compiler available in 1958, 1957 or something. Then your Fortran program comes after that, maybe 50 cards here. And then you say to the computer, load my program and run it, and this is my data for the program, okay? So this is a deck of cards. You should not change the order of the card because it's very important. So you have 200 cards, and it has to be punched by yourself. Once you punch your cards, okay? Once you punch your cards, you take them, you give them to an operator. This is a person responsible for taking the cards, and it puts them into this card reader. It's a mechanical device. It reads all those punch cards, and this is a computer, very simple computer. It is very good. This is a very powerful computer. This is like maybe $2 million. Okay, this is just a cheap computer. This is only $100,000. Okay. So you can use these kind of cheap computers for $100,000. You can use these kind of cheap computers to do these kind of simple tasks. Otherwise, I have to spend the time of this computer. Okay, so I don't spend the time of this computer. I read these cards and I put those programs onto tape drive. Tape drive is something like that. Okay, it's a tape. So maybe a few hundred meters of tape, magnetic tape. Okay. And all those tapes are carried by the people. This is a tape storage room. Some of them are data, some of them are programs. Okay, you take those tapes. Okay, you connect them to your computer. This is a person that takes those tapes and puts them into the main computer, mainframe. And the mainframe takes those tapes because tapes are much faster to read than the card readers. It loads your program, runs it, and it puts the outputs on another tape. Then this person takes this tape and takes it to another computer, 1401, and there is a printer connected to this one, and your output is printed. This was the case. So most of the tasks that are done by the operating system is done by these computer persons. Okay, these guys. There are many of them working in the room. This is an air-conditioned room because the computers were very, very hot. You need to cool them down, and they are working in there. Nobody can go near the computer because it is so expensive, so fragile. Nobody is allowed to use them directly. What you do is you provide your punch cards, and your punch card is read through the tape. And from the tape it is run, and another tape, then it is printed out. No screens, okay? No keyboards. You take a very sharp material like a pen, you punch your cards using that pen. Later they invented some typewriters to punch your cards for yourself, but again, no editing. You just hit a button and it it makes a punch on this card. And if you make an error, then if you make an error, this is 80 bytes of, or 80 characters of program, okay? Then you need to throw this out because you need to type it again. If you make a mistake punching this hole, then you cannot go back. There is no Control Z, okay? You cannot undo it. And this 80 characters per space, I guess it is coming from these days. I mean, if you ever wondered why are we using 80 characters per line in a program or something, I guess it is coming from those days, from 1950s. Okay, so this is the second generation. We have the punch cards. The card readers were too slow. They tied up the very expensive tens of millions of dollars CPU. So the printers had the same problem. The solution is use 3-4 computers. Each cheap computer can deal with the input-output device. Then the faster computer does the computation. So there is not much operating system again. You can run, these were all batch systems. What do I mean by batch system? This computer, all it does is, it reads a program, it runs it, when the program finishes, it reads another program. And it runs it, then it reads another program. So if it has enough tapes to read and write, then it keeps doing the same thing. There is no interaction. It's called batch processing. So there is not much operating system in that. There is not much operating system in that. Okay. So we use those cheaper computers to do this input-output stuff, and the faster and more expensive computer does the real thing. Okay. These are my cards, deck of cards. Okay, so somebody realized that maybe, I mean, during those days, people were using, I mean, what was the biggest customer for the computers in the 1950s and the 60s? The government, the military. They were doing lots of, I mean, when you need to calculate the projectile of a missile from a rocket or missile from a gun, whatever, it has to be simulated so that you would know where the missile is going to, okay? It has to be modeled. So the government the army was running some simulations. Other than that, the companies or the banks, they were running transaction processing. They have millions of people, okay? At the end of the month, you need to calculate your payrolls, okay? The government pays money to 4 million people. How do you calculate how much money you're gonna pay to them? Because there are taxes, and each year their salary changes, and each month they have different number of days they are working. Some of them take their vacation times and etc. So it is very difficult to calculate the payroll data. So those large companies or governments, they were buying those $10 million computers to calculate all that data. So they were using computers for this kind of work. Somebody realized that maybe we can use the computers to help themselves. So if you start using computer to help the computer, that means that it's an operating system. So that operating system is not useful as an output, but it is useful to run the computer more easily and more efficiently. Remember two things: abstracting the hardware and managing the resources. So those ideas started emerging in the 1960s with the second generation computers. Okay, so in 1950s, instead of coding the programs in ones and zeros or decimal points, they started using the assemblers. And at the end of 1950s, they have the high-level programming languages like Fortran. Fortran is the first high-level language, and the second one is, what is the second one? Second one is Lisp. No, second one is Lisp. Fortran is a very, very primitive high-level language, but Lisp is much more advanced. It is even more advanced than some of the languages that we are using today. It's an interpretive language, but it's very, very, it can do many things very easily. So artificial intelligence people were using Lisp in those days. So when people started using computers to help themselves, then the whole operating system field was invented and it was studied very, very carefully. Okay, in 1960s, mid 1960s, we started seeing operating systems, and we talked about memory protection, resource management. Okay, multi-programming. What is multi-programming? What is multi-programming? If you have more than one program running at the same time, okay, on the computer. No, I shouldn't say that. No, multi-programming is if you have more than one program on the computer's memory. It's a multi-programming. So if a program finishes running, then the second one runs. Or if a program wants to do some input-output which takes lots of time, okay, which takes maybe seconds, then you switch to some other program. It's a multi-programming. Then they invented this spooling. Spooling means that putting the input-output jobs in a queue, okay, like the printer queue or the input queue. A program takes care of which program should I read or write first or next. So spooling is handled by a program. By using this spooling, we didn't need any cheaper computers because since we have multi-programming, okay, spooler is a program too. So I can use this computer to run the card reader, also to run the printer too. Because this is a program and this is another program, okay? I can run the programs on the same computer with the other complicated stuff. So they eliminated this computer and this computer. So this one is directly connected to this computer and this one is connected to this computer. So what do I have? I have eliminated this person and this person, right? So I have eliminated this person. So it's becoming more cheaper and faster by using spooling. Spooling means that doing your input-output stuff with the same computer. And time sharing is similar to multi-programming. With the time sharing, the users share their time, okay? If one user of one program, let's say program A, uses the CPU for 100 milliseconds, then another program B, will use it for another 100 seconds. Then you have the C, then you have the D. It looks like that you can have 5 processes or 5 users running the same computer, but they think that they are using a single computer. They don't care if there are any users are using the same computer. This is called time sharing, and it's different. It's a little bit more advanced than the multi-programming. In the time sharing, you have your time slices. Okay, it's more advanced. Then we have Multics, as I said. Multics invented everything inventable for the operating systems. It's a very, very advanced operating system. And I think it was first used before 1970. And last time it was used, I think it was around 2000, maybe 2001. So for 30 years, they ran the same operating system for some companies. And why they stopped working on it? Because they couldn't find the hardware anymore. Because they didn't make the hardware for this kind of system. So it is not because they stopped using Multics because it was all they couldn't use it because they couldn't find the hardware to run it. Okay. So this is the third generation of computers. We talked mostly about this efficiency stuff. Efficiency is so important. If you have, okay, if I paid 1,000 Turkish liras for this one, okay, every second that I am not using this computer is money lost, okay? I am losing money because I spend so much time. I have to use it. How do I use it? People usually use these computers to do some useful stuff. If it is cheap enough, then it is okay if I don't use it during the night. But if it is very expensive, you have to use it day and night, okay, day and night. And that's the concern about the efficiency with the computers. It's very expensive, tens of millions of dollars, okay? So you need to use it days and night. Not even a single millisecond, microsecond should be spared. It has to be used. So the operating system, the management side of the operating system comes into the picture. If you have people like that doing work for you, it is very slow because people are slow, they make mistakes. So I should not people like this running the computer. The computer should be run by the computer itself, by a program which is the operating system, okay? Which is the operating system. To be efficient, eliminate all the people, those people carrying those tapes and everything, okay? And replace them with programs, which is called operating system actually. It is making the computers more efficient again, resource management, okay? Say the CPU was idle and people didn't like it. So keep the CPU busy all the time. The operating system has to find a way of switching from one program to program. Give me many programs, okay? I will run many programs at the same time, and I will not waste a single cycle of CPU time. So the cost of the computer didn't come down, but cost per user for a computer was cheaper this way. Okay, this is efficiency. And we have technology from the vacuum tubes. We switch to transistors now. Since we have transistors, we have more memory. Okay, much powerful CPUs. And since we have more memory and much powerful CPUs, that means that I can store more programs. I can run more programs at the same time. And somebody has to manage all these resources. It is not manageable by manually anymore. An automated program has to do this. So they invented memory protection. By memory protection, I mean process A cannot have access to process B's memory. Or we have virtual memory. This is memory management. This is abstraction. Each process sees the memory as a continuous space of storage place, and this memory is mine. Nobody can use it. So it's a virtual memory actually. It's not a physical memory. It's a virtual memory somehow connected to the physical memory by the operating system. We have the interrupts. You know what interrupts are. If something happens with the I/O device, input device, I don't have to wait for the input device. My process can wait in the queue, and if the input is available, an interrupt occurs, and my process is run by the operating system again. Okay, so since we have enough RAM and we have enough disk space and fast enough CPUs, then these are all good things, but they have to be managed. Okay, not a single person is using them. Okay, many persons or processes are using them. But they all have to be managed by a powerful software. Okay, so we have the beginnings of remote access with the, as I said, with the multis. Multi-programming, I talked about it. Run several programs at once. Protect each one's memory against the other. Okay, when one program needs to do I/O, okay, you will hear about this. Okay, you will hear this sentence. Okay. When you need to do I/O, that means that your CPU will sit idle because I/O devices are so slow. Your input card readers or the printers or the disk drives or the keyboard or the mouse, they are very slow compared to the CPU. I mean, if the CPU is running if the CPU can do 1,000,000 things a second, input-output devices can do only 1 or 2 things a second. Okay, think about it. So it is billion times faster than the input-output. So if your CPU waits for the input-output device, then it's a waste of time. So they found this solution, multi-programming. Load many programs to the memory. If one of the programs need to do I/O, then suspend that process. Let the other programs run until the I/O is complete. When the I/O is complete, you get the interrupt and your program can run again. Okay. As necessary, you can, okay, this is a very important term too, preemption. Preemption means that if a program is running and it doesn't need any I/O, it just keeps calculating some stuff, it is using the CPU 100% of the time, and that means that other programs will not have time to will not have time to run their program. So you preempt that process. That means that you stop that process even though it doesn't stop by itself. Okay? This is kind of time sharing. You preempt that process, let the other programs run. If they are taking too much time again, you preempt them too. So not always we expect a program to block itself for doing I/O, but sometimes the operating systems preempt CPU-bound programs to let another program run. Okay. Again, spooling is kind of a program. It's a program actually that does input-output for us. Since it is doing lots of input-output, it blocks all the time because it sends something to the printer. It has to wait for the result. So the spooling, it blocks by itself. When it blocks, then the operating system runs another program. So for the some logical diagram for the multi-programming. We have many programs. Only a single one of them is running at the same time. If this one blocks, then operating system will say that this one is going to run. Actually, how many programs are there here? How many programs do you see? There are 4, right? This operating system is a program too. So when this program stops, okay, blocks, operating system runs, and it makes a quick decision which job is going to run next. Okay, maybe this one. Then it lets this program run. But between these programs, operating system runs. That's why operating system has to be very efficient. You cannot have inefficient operating system because switching from job to job, every time operating system comes into the picture and runs some code, and that code has to be written very carefully by very educated professionals, operating system designers, and usually most of the part of the operating system, the critical parts are written in assembly to make it faster. Later they found ways of writing the operating system in much more efficient languages like the C. I mean, they invented C, the language of C, to write the operating system, Unix, right? It was their invention. It has to be very efficient, but it is a high-level language. So this is multi-programming. Integrated circuits, they gave us lots of resources like the loss of CPU time, loss of memory, loss of hard disk space, etc. And to manage all that stuff, we had operating systems, and to make the computers more efficient in terms of using even the smallest number of clock cycles, we had multi-programming and time sharing. I don't know what this is. I don't know what it is. Okay. In 1960s, in those days, the third generation computers, we have the, in 1960s, somebody, this guy Engelbart, invented the graphical user interfaces. You can see his picture in our lab actually. Where is the lab? This guy, I think he's a mechanical engineer. He was trying to do some computer-aided design CAD, like the primitive version of the operating system, AutoCAD. Okay, so he invented the graphical user interface in the 1960s, beginning of 1960s. I showed you the video actually last time, right? You watched that video. So he had everything in that operating graphical user. He had icons, he had menus, and he has a mouse too. Okay, so he invented everything inventable for that respects. But it took some time to use that kind of technology with the computer. So I think it was the 70s. People started using those icons and menus and mice in a computer. Then Apple took that idea in 1980s and it started using them in microcomputers, personal computers. Nowadays everybody is using those, right? Nowadays everybody using those kind of ideas. So the main idea was invented, those touch screens, mouse, user interfaces and everything. It was invented again in the 1960s. Okay, nowadays we have mobile operating systems and mobile computers. I think the first smartphone was, let me go to, okay, it is not, okay, let's take 10 minutes of break and I will try to fix this problem. And you're out. Okay, let me, okay.